right, good morning everyone, and once again welcome back to algorithms and data structures. First things first, can you all hear me and see me? Let's figure that out. Also, let me check this. Yes from Alfie, that sounds good. Yes from Famosos, however you're supposed to pronounce that. Also, okay, excellent. Good. Then once again, good morning, everyone. Let's see how things go today. So, like I announced yesterday, today will be another regular lecture. Or regular lecture, as far as anything can be regular via Twitch. Which means we'll be using feedback fruits. Our code today is QLW, which I will also link in chat here. And today is going to be about minimum spanning trees. So hopefully you remember that yesterday we took a look at topological orderings as well as shortest path algorithms. Today then is all about minimum spanning trees and two properties related to that, and they are properties of graphs. That are very nice for forming our algorithms for minimum spanning trees. And that leaves one more topic for next week, which is P versus NP. And of course, still the exams at some point in the future. I'm afraid I still don't have any news on that. I have just read that hopefully by the end of today, I will be informed about it. And as soon as I have anything that I can share with you, I will do so. So hopefully by Thursday at the latest, we know how this is going to work. Before we begin, one question. Yesterday I tried to send the emails from Zesje, the system I've used to grade your written exams. I've tried to send them again. Did you get them this time? So you should have an email with a PDF of your written exam. I see a number of people saying yes. Good. Okay, the trick that I applied worked. Okay, excellent. So same thing applies for the computer as for a computer exam, right? If you have any questions about the way you've been graded, please send me an email at the course email address, and I'll take a look as quickly as I can. All right, good to hear that worked. Then, before we get started, are there any questions from your side? Anything you want to know about the course, about yesterday's content, anything at all? So far, nothing. I'm gonna give it another couple of seconds. All right, then let's get started. So today is going to be about minimum spanning trees. Yesterday was about shortest path algorithms, and we saw two of them. We saw Dijkstra, a very efficient algorithm. When we use a priority queue, it was v plus e log v. That was pretty good. It required no other contextual knowledge. It was just give me a graph, give me weights, and I can go for it. Downside was that because we require no context, we can also not exploit the context. And with that idea, we also looked at A star, which uses a heuristic to improve performance. So some sort of estimate of how far it will be from one node to the end. And by doing that, if we have a very good heuristic, we can reduce the number of nodes that we take a look at. The downside, of course, is then that I need a good heuristic, and this heuristic had several criteria. There was something about our estimations must always error to one side. We must never underestimate, right? And Must never underestimate, must always underestimate. Let me think. Manhattan wasn't a good idea when we could go there directly. We must not overestimate, so we must always underestimate. Yes, because 0 will always work. Yeah, we must always underestimate. And the downside then is that this requires contextual knowledge. Okay. So Dijkstra and A star, both the same runtime complexity, but depending on whether we have this contextual knowledge, we can reduce the number of nodes we visit and thereby improve our runtime. And anecdotal evidence from some video game developers told us that sometimes this can lead to a factor 2 speed increase. That's pretty good. Okay. Let's take a look then at our question for today. So remember, we were working down this list of questions, right? What cities can you reach? BFS, DFS. What's the quickest way? Dijkstra or A star. What's the best way to connect new stations to the network? Well, this is something we can solve using minimum spanning trees and something that we're going to take a look at today. And that leaves how can we quickly tour the entire country for next week. Although I hope that time allows for me to give an introduction to complexity theory, so to P versus NP, already today. Okay, let's talk about the internet a little bit again. So yesterday we talked about the internet in our Intermezzo and about how there are different routing algorithms that we can use there. But let's talk about the machines in the internet and how they are connected. Because we have a lot of these routers out there in the world. And if you want to set up a new network in, for example, an office building, this is a question you might be asking. Given n machines and m possible connections between them, all with a certain cost, for example, the length of the cable, what is the cheapest way to connect the machines such that the message can be sent from any machine to any other? And that doesn't have to be directly, right? Because if it's directly, that just means every machine needs to be connected to every other machine with an edge, with a cable. But indirectly is fine. So if we have 3 machines, then we can go from A to B and B can forward it to C. So with just 2 cables, we can connect all of them. We call this a strongly connected graph, if you recall. And that's the problem we are going to be solving today. Now, of course, this works for machines and cables. It also works for stations and railways and a variety of other applications. Example, here's a graph. What is the minimum cost here to connect or to make this graph strongly connected? Right, so what cables should I lay, if you will? What connections should I make to have a strongly connected graph? Our code for today is QLW. You have about a minute and a half, and Feedback Fruits is happy to hear your answers now. Okay, let's take a look. 12 is the most popular answer. And then about a fifth for 13 as well, very close together. Let's take a look. By the way, before we do, I ordered a webcam some time ago because while using my phone as a webcam is clearly not ideal. Not only are there desyncing issues between the video and the audio, but also all kinds of other stuff. Unfortunately, due to some delays, well, I don't know when I'll be getting it. So it might be too late for this course, but I hope that a better camera is on the way. Anywho, minimum cost for a minimum cost for laying these cables. What can we do? Well, F, C, and B, D, F can all be connected to C relatively cheaply. So maybe we should include those. That's 6. Then we still need A and H. Well, together, putting them together may cost us 3, and connecting them to D costs us 3. So that would get us to 12. So we can definitely do it in 12. Can we do it any cheaper? Well, we have 2 8s, a 9, and a 4 left. Those are all larger than the ones I picked. So no, the best I can do is these edges for a total cost of 12. And now indeed it is possible for any machine to send a message to any other machine. Right? If A wants to send a message to F, it has to go through some other machines, but it can definitely get there. Does this idea make sense? The problem is clear? I see no questions about it. Couple more seconds just in case. All right. Okay. So this is the problem we're trying to solve, right? Connecting machines, connecting train stations, whatever have you. Well, to do so, we're going to look for a spanning tree. So a spanning tree of a graph is a subset of edges such that a graph containing only these edges, so exactly the same vertices, but only this subset of edges is still strongly connected. And it's also a tree, right? Furthermore, a minimum spanning tree is a spanning tree such that the cost, so the sum of the edges that we've chosen, is sum of the weight of the edges we've chosen is minimal, meaning there is no spanning tree with a smaller weight. There could, of course, be another spanning tree with the same cost or the same weight, but there are none smaller. So there could be multiple minimum spanning trees, but none with a smaller weight. Okay. Minimum spanning trees. How do we find those? Well, let's take a look at a very nice property. We call it the cut property. So the cut property is the following. Take any subset of vertices in a weighted graph. Now let E be the minimum cost edge with exactly one endpoint in this subset. So we have a subset of vertices. Now take the smallest edge, leaving that subset of vertices. The cut property states that there must be an MST that contains this edge. Remember, an MST is not necessarily unique, but there must be a minimum spanning tree that contains this edge. Example. Say that the vertices highlighted in red here are my subset. C, F, A, and H. So you can imagine some sort of shape being drawn around it, right? Now consider the smallest edge leaving this subset. Which one is that? And so which edge must be in an MST? Can you tell me that? Which edge is the smallest one leaving this subset S? Siroi, CD, also CD, Jan, yeah, with a weight of 2, exactly, so also the edge CD. Yes, remember that the official notation is between parentheses, right? Sorry, it's an undirected edge, between curly braces, right? But yes, it is indeed the edge between C and D. So, I'm also doing it wrong here, should be curly braces. The edge CD must be in the MST. It's an undirected edge. Let me make a note to fix that later. Slide 9, curly braces. Okay. Okay, so we can use this cut property to find some edges that must be a part of the MST. Great. Well, that's great, provided the cut property is indeed true. So let's quickly prove it first. Now, consider an MST that does not have this edge E. Right, so E is still the minimum cost leaving this subset. Well then, when I add E to it, I must create a cycle. Why is that? Well, a minimum spanning tree has is a tree, and as soon as I add one more edge in there, I must have created some cycle, because at first I had n-1 edges, and now adding one more gives me a cycle, right? Or another way to think about it is we have this subset S. Inside S, we must be spanning all the nodes. Now we have an edge leaving it. That's not in the MST, yet this subset must be connected to the other nodes in an MST. So there must be another edge leaving this subset S. So if we have one going out and another going out, then two of them are going in. So we must have created some cycle. Which means that there's another edge F, that connects this S to the rest of the vertices. Now, the weight of E must be smaller than or equal to the weight of F, because E was the minimum cost edge. So, consider now the tree in which we remove F and put in E. It has a cost that is no larger and is still a spanning tree. And so this is a minimum spanning tree that contains E. Right, so imagine that we pick another one, then we say, well, we could replace that one with E without making the costs larger, therefore that must still be a spanning tree, a minimum spanning tree. Okay, so the cut property is true. It says take any subset of vertices, the smallest edge leaving it must be part of an MST. Now, two people independently discovered an algorithm that uses this property to build a minimum spanning tree. Someone we talked about yesterday, called Dijkstra, and someone new called Prim. However, something that is often overlooked, unfortunately, is that both of these actually rediscovered an algorithm that was discovered earlier by the mathematician, no idea how to pronounce this, sorry, Jarnik, who invented it about 30 years earlier. And this algorithm, which should of course have then the name maybe Dijkstra PrimJarnik or something like this. Well, they said, well, Dijkstra, you already have an algorithm, you don't get another one. So we call it the PrimJarnik algorithm. And the idea is that it's very similar to Dijkstra, right? So we have some sort of cloud. And what do we know now? Well, this cloud is a subset of vertices. And the cut property says the smallest edge leaving this subset must be part of an MST. So what do? Well, we just take the smallest edge leaving our subset and we add it. And by repeatedly doing this, we must in the end up with an MST. Now, unfortunately, so I will try and always call it PrimJarnik, but many people just call this Prim's algorithm to make the injustice even greater. So Prim or PrimJarnik is similar to Dijkstra, we have some sort of cloud of vertices that we're growing, and we're using the cut property to say every time we have this cloud, the smallest edge leaving it must be part of an MST, so that's the next edge we add. So what I've done here is I've taken the code for Dijkstra and I've highlighted the 4 changes we need to make. That is all. So what do we have? Well, we need to keep track of the cost of our minimum spanning tree, which in the end we also want to return. We need to keep track of, or we need to update this. Every time I add a vertex, I add its cost. And the cost to get to a vertex is now no longer the cost to get to the previous vertex plus the weight of an edge, but it's only the weight of this edge. So let me do it like this. We only check the weight of the edges in PrimJarnik's algorithm. And why is that? Well, again, we have this cloud and we just want the cheapest edge leaving the cloud. We don't care how we got to this point. That's relevant for finding shortest paths, but not for this cut property. This cut property only says, give me a subset, shortest edge leaving it must be in the MST. So that's all we're doing. We're only keeping track of the shortest edges leaving, or we're only keeping track of the edges leaving the MST without any cost in getting to such a vertex. Are there any questions about PrimJarnik's algorithm? One of my colleagues who's very much into languages has tips on how to pronounce the name. If you pronounce it as if it is Dutch, you get pretty close to the Czech pronunciation. So sounds like in goed, okay? So Vojtech would be then, I'm not sure what to do with the Vojtech, I'm not sure what to do with the J, but thanks, Frank. Any questions about PrimJarnik in the meantime? Doesn't look like it. So then I suggest we move on. Okay, so let's apply it. So here we go. Here's the graph that we did Dijkstra on yesterday to find the shortest route from A to I. Now let's find a minimum spanning tree of this graph, and please try to do so using PrimJarnik. Yannick, whatever works. I will give you, let's say, oh, I see I never reset this one, 2 minutes to try and make this work while I get my tablet set up again, and then we'll take a look together afterwards. Okay. Let's see if this works. Looks like it is working. Here we go. Okay, so let's see if we can figure this out, and if we can figure this out, of course, using PrimJarnik's algorithm. So what do we have? Well, we have the same graph as yesterday, so let me quickly copy it here. B, C, F, K, H, I, J, D, 9, 2, 4, 2 edges of weight 8, 1, 1. That's a horrible looking one, but okay. 2, 3, 1, 1, 12, 3, and 2. Okay, let's apply PrimJarnik, which means that once again we're going to need our little table with vertices and some distance. We also need to select a vertex to start from. Now, I don't really care. S for Stefan is not an option. So let's take the first letter that appears in my name. Let's take F. Okay, we're going to start with F. So A, B, C, and I need to hide the tablet for just a second because an ad is going to pop up any second now. Sorry for this. I've tried to look into buying the license, but it only allows me to buy a license for the rest of my life for 50 euros. And that sounded like quite a lot of money for something I just want to use for 2 weeks. So we'll have to make do with me hiding the tablet every now and again. But we're back, so let's see if we can do this now. So F starts with a cost of 0. I'm not going to put in the infinities. Just assume that if the cell is empty, it still contains infinity. Now, PrimJarnik's algorithm. Once again, just like yesterday, let me open the algorithm on the on the slide. We take a look at all of the edges or all of the vertices we can reach from F. So we can reach K and I and H, and we update them with this smallest edge. Now we take the smallest one, which is K. There we go. And we update. Now remember, in Dijkstra we would say, okay, it's the distance to K, that's 1 plus 3 is 4 to get to H. But in this case, we're not doing that. We're only considering this new edge 3, right? We're looking for the smallest edge out of this set of points, set of vertices. And that is still the edge between F and H. So we do not update this, but the next thing we look at is H. And now we have one more. We have I with a cost of 1. Again, it's not 2 plus 1, it's just the 1. I is now the smallest. So we go to I. I meant to put the check mark here. Now we have a new cost for J, it's just 1. So next thing we do is go to J. Is this gonna work? Did I? Ah, of course. Now it's not directed anymore. Hang on. Oh, dang it. Okay. That's gonna be... why is my eraser not working? Hello? Okay, let me do this differently then. I'm not gonna need red, so let me just make that black. Right, today the graph is not directed, right? Yesterday when we did Dijkstra it was, but now in our minimum spanning tree, we're just looking for an undirected at looking at an undirected graph. Okay. That means we need to update a couple of things. But not to worry, we can make that work. Almost done removing the arrowheads. This is where I missed the smartboard. I would be able to do this a bit quicker there. Okay. Because when we were at F, we were also going to take a look at C with just a cost of 1. Which means that after K, we would have taken a look at C, which got us a cost of 8 to D and a cost of 2 to B. Which means that when we took a look at H, we would, no, then it would still be fine, because now we have costs of 1, which are definitely smaller. Okay, so now we're at J. Let's update everything. We have a cost of 12 to A now, of 3 to D, so that's quite a bit better than the 8 we had, and of 2 to F, but F was 0, so that's not going to be better. C we already have completed. Now let's pick the smallest one. The smallest one is a 2 for B. So we consider B. This gives us 9 to A. So our 12 becomes 9. And now we take the smallest one out of A and D, so that's D. And we update A to become 4. And so we go to A. There we go. And now we're done, right? We've considered all of them. And something we should have been doing in the meantime is keeping track of the cost, right? The cost was we added the distance to our vertex every time. So this is C plus equals dv. Well, okay, I forgot to do that, but not to worry. My table now contains exactly the edges that I want, or rather the costs of the edges that I want. So if I just sum all of these together, 1, 2, 3, 5, 8, 9, 11, 15, then we get to the answer that I was looking for. So the answer here was 15. I just realized I never opened it in feedback fruits, but that's okay. Hopefully the explanation still was clear. Any questions about this application of PrimJarnik's algorithm? Silence so far. I'll give you a couple more seconds to account for the stream delay and the typing delay, but otherwise we're gonna move on. Ah, very good question, Ulrich. If we were asked to do this on an exam, how should we annotate what we're doing? So if I were to ask you this on an exam, I would ask the question in such a way that I can easily check your answer. So for example, what I could ask is, give me an ordering in which PrimJarnik's algorithm could go over the nodes, right? Starting from some node, F in this case. And then I would just expect F, and then what's the next one we did? So K, and then it should have been C, and so on and so forth. Right? So if I were to ask you to demonstrate this algorithm, I would do so in a way that makes it relatively easy for me to check. So I would say start it from this node and give me the order in which you consider the vertices. Something like that. Does that make sense? Excellent, good. All right, then let's move on. So let me hide the tablet again. Let me make the slides a bit bigger again. There we go. So, what's the runtime of this? Well, it's the same thing as Dijkstra, right? Only thing that it's different is that we need to keep track of this extra counter for the extra summation for the cost. Well, that's just some constant time adding some extra stuff, and we need to update the weights differently, but we still need to update them. So the runtime is the same as in Dijkstra's algorithm. So v plus e log v, when we use one of these priority queues as we saw yesterday. Okay, that's PrimJarnik. It's one way to handle this problem. Now let's take a look at another cycle property, or another property of a graph, which is called the cycle property. So we saw the cut property, right? Given a set of nodes, the smallest one leaving must be in an MST. Now consider the cycle property. Take any cycle in a graph. Doesn't matter which one, pick one. Now take the edge in that cycle with the largest cost. This edge is guaranteed to not be in any MST. So consider a cycle, which is not highlighted in red here, but consider the cycle A, B, C, and D, right? The cycle through these four vertices. Which edge is then not in the MST? Yes, in perfect notation this time. Thank you, Jan. Yes, indeed, the edge between A and B cannot be in an MST according to the cycle property. And again, I did the wrong notation here. So AB is the edge with the largest weight in this cycle, and according to the cycle property, that means it cannot be in there. Now, the great thing about this cycle property is that in a graph like this one, where there are a lot of cycles, we can eliminate a lot of edges, right? So for example, we have a small cycle over here between C, D, and F, so we can eliminate this edge, and we have a cycle here, so we can eliminate this edge. We can construct a cycle like this, so we can eliminate this edge, and by repeatedly doing this, we can get very close to the MST that we just drew up. To an MST that we started with, right? When I asked you what's the smallest one for this graph, and it was the one with 12. Now, again, before we base an algorithm on this idea, let's check the idea. Our proof is similar to the one for the cut property, right? For the sake of contradiction, take an MST that does contain this edge. And let's give the endpoints of this name. Let's give them names. The endpoints of this edge. Let's give them names. So let's call them U and V. Now take this MST and remove E from it. That means that we now have two disconnected components, V1 and V2, where U is in one of them and V is in the other. So let's just say U is the one in V1 and V is the one in V2. Now, what does that mean? Well, if I now need to reconnect V1 and V2, there must be some other edge there that could do the job. After all, E was part of a cycle in the graph, so there must be some other edge that connects V1 and V2. However, the cost of this edge must be smaller, because E was the one with the largest possible weight in the cycle. So if I add F to my set T, then I now have a set of edges that costs less. and therefore I have created an MST that is better, and this is a contradiction, because an MST has the property that there can be no spanning tree with a smaller weight. Right, so it's a very similar proof to the one of the cut property. The idea relies once again on the fact that if I have two parts, if I take this edge and I replace it with another one, in the cut property we saw that this would make it worse, and here we see that that must make it better. Therefore E cannot be in an MST, and with the cut property the conclusion was E must be in an MST. Alright, we're a couple minutes early, but I suggest we have our break now, before we delve into an algorithm that is based on this property. So after the break, we will be discussing an algorithm that is called Kruskals algorithm. And I'll see you back for that in about 15 minutes. Just like yesterday, I'll stick around in chat during the break, so if you have any questions, feel free to ask them there. And otherwise, I'll see you soon. right. Let's try and get started again. Now, just after the break would normally mean that it's time for today's intermezzo. But today's intermezzo is, well, not really an intermezzo. It's going to be at the end of the lecture when I tell you a little bit about complexity theory, which we will be studying just a tiny bit of next week. So we'll end with that today rather than having it in the middle. Okay. So, don't worry, it's going to be fun story time all around, or at least I think they're fun, and I hope so that you think the same thing. Let's talk about Kruskals' algorithm then. So Kruskals' algorithm is another way to find the minimum spanning tree that is based on this idea of the cycle property, that the largest edge in a cycle can never be a part of a minimum spanning tree. So consider, for example, in this graph, the cycle ABD, ABDA technically. The edge between B and D has cost 9. It's the largest one in this cycle, so it can never be part of an MST. Now, how does Kruskal work? Well, it says first sort the edges by their weight. And now consider them in order, starting with the smallest one. Add it to the minimum spanning tree, which in accordance with the cut property is what we should do, right? Given a subset, smallest edge leaving it should be in there, unless it actually creates a cycle, because then I must have added all the cheaper ones in that cycle already. So this one is the most expensive one, and therefore I don't want it. So I discard it as dictated by the cycle property. That's the idea for Kruskal. Let's see if we can put that into code. So step 1, sort the edges ascendingly. Label them edge 1 to edge M. Now, repeatedly, so this is the while loop, repeatedly, if adding this edge does not create a cycle, then great, I found another edge, I add it to my minimum spanning tree, and I continue on to the next edge. This line should be outside the if statement, right? We always continue to the next edge. Otherwise, we get stuck if there is an edge that does create a cycle. So this line should be outside the if statement. Slide 23. Okay. Two things to note here. Let's start with this while loop. While k is smaller than v minus 1. Okay, the size of v minus 1. So the size of v minus 1, what does that mean? It means that I want to connect all the edges, or sorry, all the vertices without creating any cycles. And so indeed, I must have at most v minus 1 edges. And when I have exactly v minus 1, I'm done. I have created a spanning tree. So that's the first thing, right? Connecting all the vertices requires exactly v minus 1 edges. And the second thing is this, if it does not have a cycle, how can we check for that? How can we efficiently determine whether adding an edge creates a cycle? Well, let's try some ideas. How about we try something based on IDs? What is the idea here? Well, every node keeps track of, let's say, a cycle ID, right? What cycles it is a part of. And to start with, we just say, well, you're only in one very small cycle, a cycle with yourself, if that makes any sense. Basically, you're not in a cycle is what this represents, right? Then, if I put two nodes together, meaning I add an edge between them, this is only allowed if their cycle IDs are different. So this cycle ID is some sort of subset that it's a part of. And then I update both IDs to be, well, one of the two, so let's say the maximum of the two, to indicate, well, look, these two I have now grouped together. Unfortunately, this doesn't work. Now, normally I'd ask you to draw something on the whiteboard that we have in Pulse to come up with a counter example. Now I don't think there's a very good way of sharing images between the two of us, well, from your side to my side. So I'm afraid I'm just gonna show you. So let me get my tablet visible again. Here we go. And make this slide a bit smaller. So, like this. Okay, let's have all of the vertices start with their own ID as their cycle ID. And now let's add two of them together. Let's say I add these two together. Now what do? I update the cycle ID to the maximum. Okay. Now what do? I add these two together. So I update the cycle ID to the maximum. I add these two together, which is perfectly allowed. Their cycle IDs are still different. I update to the maximum. And here you can see why this is going to break. Because now, when I try to add these together, their cycle IDs are still going to be different. This one has a cycle ID of 2 and this one has a cycle ID of 4. So I can safely add these together according to the cycle IDs, but this does actually create a cycle. So this breaks. So you might think, okay, so what we actually need to do is when I added this yellow edge here, this thing, I needed to make sure that instead of only updating this one, I also update this one. But that becomes a whole lot more tricky because now I need to keep track of what other vertices are in there, and adding just one edge could ensure that I, worst case, need to update a large number of vertices. And that's when we start to lose this idea of efficiency. Remember, this whole idea of Kruskals is only really worth it if we can do better than PrimJarnik, or at least just as good, right? And if for every edge we add, we need to check all the vertices, that performance is going to go down the drain. It's going to be E times V, which is worse than E plus V times log V. So this idea of cycle IDs isn't quite going to work. Let's see if we can come up with something else. And fortunately, we can. We can come up with something else, but for this other thing, we need to look at a new data structure. And this new data structure is a data structure we call the union find data structure, also called the disjoint set data structure. So union find or disjoint set is a data structure that can track elements partitioned into disjoint subsets. It provides near constant time operations for merge and contains. Okay, near constant time, merge and contains operations, and it's all based on disjoint sets. That sounds exactly like what we want, right? To start with, every node is in a set of its own, and when I add two of them together, they should become part of the same set. But all sets should remain disjoint, because otherwise we may have created a cycle. This is starting to sound promising. Let's see how we can make this work. Right, so Kruskal just creates a bunch of sets, and they must never contain duplicates. We need to merge them when adding edges, and we need to check if they are in there to avoid cycles. So this merge and contains is all we need. And if these can be done in near constant time, that sounds great. So what does a union find or disjoint set allow us to do? Well, it allows us to initialize the data structure with make set n, which creates n initial sets all containing exactly one element. It allows us to return the ID of a set that our element x is in. And finally, it allows us to merge two sets that x and y are in. Right, so these are the three operations that the union find data structure supports, or the disjoint set data structure. Let's take a look at that implementation. We have, for every element, we create a set of size 1, so it contains only one element to start with. And then there's this notion of rank that we'll come back to later. But for now, we initialize all of them to 0. So the bottom line here is that for every element, we indicate what set they are a part of. And to start with, every set is part of only, or every element is part of its own unique set. So every element has their own ID as an identifier. All right, then what is find going to do? Well, skipping the if statement for a second, find is just going to tell us what set it is in. So given our element x, we just return the set ID of that element. Now there's one extra thing we do. We apply what we call path compression. In a moment, we're going to be joining these sets in some way. And this path compression in find allows us to make sure that if I find the element again, this can happen a little bit faster. I'll show you an example of what this means in a moment. So let's get into the bottleneck of this whole thing, our function union that merges two sets x and y. What is it going to do? Well, first it's going to find out what is the set that x belongs to and what is the set that y belongs to. Now, if these are the same, if they are already in the same set, there is nothing for us to merge. And this is where the rank comes in. If the rank of the set x is smaller than the rank of the set y, then we add all of x to the set of y. So we have the rank is some representation of size, if you will. We have a smaller set and a larger set. If x is the smaller set, then we add x to the larger set y. If it's the other way around, then we add the smaller set y to the set x. And if they are the same, if they have the same rank, same approximation of the size, then we now say, well, we've added it to x, so x should become a little bit bigger. Okay, quite a lot to take in, I think. So here's what we're going to do. We're going to practice with this a little bit. I'm going to show you the first few, and then I'm going to give you a few more to do based on where we leave off with this. So let me get my tablet out again. Here we go. To start with, we have 10 sets, all containing just one element. And here's how we're going to draw that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Quickly hide the tablet for the poker ad. Wait 5 seconds for me to reopen my Blackboard. There we go. Okay. To start with, we just have 10 sets on their own. Now I'm going to union 1 and 8. So what's going to happen? Well, we're looking for the sets that 1 and 8 belong to. Well, 1 belongs to the set 1 and 8 belongs to the set 8. These are different. So we add 8 to the set 1. And this is usually how I visualize that. We have the set of 8 point to 1. Furthermore, this remains unchanged, but the rank of 1 has now become 2. Because their ranks were equal, so the rank of x is increased by 1. This is what the if statement in our pseudocode says. Okay, we have now unioned 1 and 8. Let's take a look at the next union. 2 and 4. Well, exactly the same thing. 4 becomes goes and points to 2. This has not changed. And the rank of 2 has also become 2. Now we union 4 and 7, and things become a little bit more interesting. Because when we union 4 and 7, what's going to happen? Well, we get, so in our code, we first get the sets that they belong to. Well, 7 still belongs to 7, but 4 belongs to 2. So we check, are 2 and 7 the same? No, they're not. Okay, is the rank of 2 smaller than the rank of 7? No, it's not. So we add 7 to this one. And that means set of 7 now becomes 2. Now we union 3 and 5. 3 and 5 are simple to union. This remains unchanged. But this rank becomes 2. And notice that the rank is an imperfect measure of size, right? Because 2 now has 3 elements in its set, but its rank is still 2. So it's just an approximation of the size, and it's a good enough approximation. Now I want to merge 9 and 5. Again, the set of 5 is now 3, meaning what's actually going to happen is that 9 points to 3. And finally, I'm going to merge 5 and 2. And now it becomes really interesting. Because what's going to happen? Well, both of them, of 5 the set is actually 3, and of 2 the set is 2. They both have a rank of 2. So, according to our code, we make 3, white please, or let's do green for this more complicated one. We make 3 point to 2. So we update this to become 2. And we update this to now become 3, right? We've merged 2 of the same rank, so the rank gets increased again. Now consider what happens when I call find 3. Well, find 3 will just return 2, the set it belongs to. Now, find 2 will just return 2. Now consider what happens when I call find 3. Well, if we take a look at our pseudocode of find, what it's going to do is it's going to check, okay, am I the owner of my set? No, I'm not. Then I should find whatever it is, the thing of 2, and that's 2, so I return that. Now what happens with 5? Well, the set of 5 is still 3. 3 does not equal 5, so it checks 3, which checks 2, which returns 2. But the crucial thing here is that we also update set of x at that point. So as soon as we've done this find operation, this 3 has become a 2. Meaning that next time we do this, we can leave this call out and only go for find 2 to get us 2 immediately. Which means that the next time I call find on 5, I am a little bit faster in finding my solution. That's that idea of path compression. This arrow that is pointing from 5 to 3 is now directly pointing from 5 to 2. And the same will happen when I call find 9, right? This arrow from 3 will be updated to directly point to 2. And that is this is one of these operations that allows us to make union find such an efficient data structure. This notion of path compression. Now what I'd like you to do is take wherever we now left off, and over the next 2 minutes or so, try to perform 3 more operations for me. So first we'll just do find 5 because I've already done it. And now please union 6 and 1 for me, union 10 and 8, and then union 8 and 3. I'll give you about 2 minutes to do so. And if you have any questions in the meantime, feel free to ask me. All right, so let's apply these operations. So find 5, as I mentioned, I already applied. So let's move on to the next one. So the next one, union 6 and 1. Okay, unioning 6 and 1. What does that mean? Well, it means 6 is going to point to 1, and the set of 6 is therefore 1. Union 10 and 8. Okay, 8 is already pointing to 1, so 10 will point to 1, and the set of 10 will become 1. Now union 8 and 3. Okay, this looks like it is going to be a bit more complicated again. 8 and 3. So 8 is in 1, 3 is in 2, so what we're actually unioning is 1 and 2. Now the rank of 2 is larger than the rank of 1, meaning 1 will be pointing here, and its set will now become 2. And now when I call find of 8, the first time it will call find of 1, which will call find of 2, which will return 2. But the second time I do so, this will be crossed out because this will be updated to 2, applying our path compression. Now, union find is usually a bit tricky to get your head wrapped around. So I can imagine that even just seeing it once now might be a bit too tricky, which is why on Thursday in the tutorial we will also be implementing the union find data structure to get a bit of extra practice in with how this thing actually works. That being said, are there any questions now about this application of union find on these 10 sets? Would the rank of 2 not change in that last step? Very good question, Ur. The answer is no, because the rank of 1 is still 2 at this stage, whereas the rank of 2 is already 3. So they are different. And we only update the rank when the 2 ranks are the same. Famos with union 6-1. Shouldn't you be updating the rank of 1? No, so same deal. 6 wasn't in any set yet, so it still had a rank of 1, meaning it's smaller than 2, and we again only update when they are equal. And this is why this rank is really an imperfect measure of size, right? It doesn't contain exactly, or it doesn't portray exactly how many elements are in there. It just gives us some idea of how often merges of equal size happened. But again, that's good enough for the union find data structure. Okay, that seems to have answered the questions. Good. And then let me transition us back to the slides. Move this over here so that I can still see Twitch chat when looking at the full screen slides. There we go. Okay. Now, with all that said and done, we should be able to apply Kruskal on this graph. I'm not gonna yeah, actually, sure, why not? So remember, Kruskal, what does it do? Kruskal sorts the edges, considers them smallest first, it adds them to the MST if it can, but if it would create a cycle, then it will not add it to the MST. And we can use union finds to keep track of whether they are a cycle or not. I suggest we leave that part for now. Instead, we focus only on Kruskal. So we can visually see whether adding the edge would create a cycle. So for now, let's say that's good enough. And we'll focus on the union find part a little bit more on Thursday. I'll give you, let's see, 1 minute 30 to answer the question, and Feedback Fruits is happy to hear your answer now. Sorry, time has already passed. I was quickly working on something else. Let me take a look at your answers. Oh, the slides have also closed. That was not my intention. Sorry for this. Let me reopen the slides. Kruskals is what we were talking about. And we were applying it on our graph. There we go. Let's take a look at your answers. 10 is the most popular option, but 12 is close behind. So let's take a look. What does Kruskal do? Well, I have already drawn the graph for us. If my tablet is willing to cooperate and go back to that slide, that would be amazing. Hello, tablet. Yes, there we go. Let me also show you the tablet. That's the help. There we go. So we have our graph here. What's Kruskal gonna do? Well, it's gonna check them in order of increasing weight. So to start with, it checks this one, and it can safely add it without creating a cycle. Now it might go for this one. It can safely add it. So let me actually draw in green the ones we are adding. Now it might check this one, right? Anything with cost 1 is still at this point an option. It might check this one. Now it's going to move on to the edges of weight 2. So it could add this one. That's fine. No cycles are created. This one, however, would create a cycle. So Kruskal does not pick this. It moves on. The next one with 2, that could be this one. That does not create a cycle, so it's fine. Now weight 3, so it can select this one. However, again, this one it will not pick, because picking it would create a cycle. Are we done? No, not yet. We still have this node A here. So we take the next smallest edge, which is weight 4. Now we have n-1 edges, which means we terminate our algorithm. We are done. And we find the same weight for our minimum spanning tree as PrimJarnik found us before. So how many edges did we consider? Well, let's quickly count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So answer A, 10 edges, is indeed the correct answer. All right, let's see here. We have a new idea for an algorithm. It's Kruskal's algorithm. But what's the runtime? Is it worth it? Did we make anything better compared to PrimJarnik? Well, union find is a very nasty data structure to analyze. In fact, the analysis of the data structure is outside the scope of this course. But I hope you'll trust me when I say that we can do M union or find operations on n sets in M log n time. There is a very nice and fancy analysis of this data structure you can find on Wikipedia or other sources if you're interested, but for today, this will have to do. Now for Kruskal, we have V sets, every vertex is a set, and we do at most E unions, namely one for every edge. Furthermore, we need to sort the edges, that's E log E. So the runtime is E log E. And well, E is at most V squared, so we could bring this down to E log V if we want, because V squared in a log is just V. Remember, squaring something in a logarithm is the same as multiplying by 2, and multiplying by 2 is just multiplying by a constant, so we don't care in big theta. So Kruskal we can do in E log V. What does that mean? That means that we've seen two algorithms to find the minimum spanning tree. PrimJarnik, which is like Dijkstra, and we just repeatedly pick the smallest edge out of our cloud. And Kruskal, which repeatedly picks the smallest edge, not out of our cloud, but the smallest edge in the graph, and we add it so long as it doesn't create a cycle. Both offer very good runtimes, v plus e log v and e log v, but they have their own special, cases that are a little bit better. So Kruskal, for example, is quite a lot better if the edges are already sorted for whatever reason. PrimJarnik we can improve by using a way more advanced priority queue, again one that's outside of the scope of this course for you to implement, but it does exist, which would allow e plus v log v time, which means that it's quite a lot better when e is much larger than v. Right? So when we have many more edges, PrimJarnik might be better. Intuitively, perhaps that also makes sense, right? PrimJarnik operates more on a vertex-based system, whereas Kruskal operates more on a edge-based system. So maybe the intuition you can apply there. Okay, now that means that today we have solved one more problem of DNS, namely connecting new cities to our network. If we have a bunch of cities and we want to connect them, we can find the minimum spanning tree to do so with minimal cost. Great. That leaves us with P versus NP for next week. And I have about 8 minutes left now, and I want to give you a small introduction to that topic, based on some slides that I use at the Open Days for Computer Science. Now, of course, before I do that, let me quickly wrap this up. So you can now read chapter 14.7 in the book, which is about minimum spanning trees. Before Sunday, you can do the homework, which is available. And please make sure that you check the feedback on your written exam and let me know if you have questions about it. Okay, let me switch us over then to my introduction to P versus NP. So at the Open Days, I tell this whole story about reasoning and logic, a course that is somewhat similar to mathematical structures. I talk a little bit about propositional logic and about predicate logic. And then I say, well, we teach you much more in this course. For example, we will teach you how to prove statements like this. I tell the whole story of Gauss in his childhood, outsmarting the teacher by simply adding the numbers from 1 to 100 by using this trick, yada, yada, yada. And I showed them that, well, we can use mathematical induction with a lot of math and a lot of English to show that something like this can be done. Now you know this. You've learned this in mathematical structures. I have then told you a little bit about stuff like this, about graphs, about finding the shortest paths in these graphs, and about minimum spanning trees in these graphs. I've also told you about BFS traversals, DFS traversals, and topological orderings. And now that you've done all that, you are ready for what I would call the ultimate challenge in computer science. Now, if you ask my colleagues, if you ask Frank, who was in chat earlier, they might give you different ultimate challenges in computer science. That's okay. We all have our own favorites. But to me, the ultimate challenge in computer science requires you to imagine that you are this guy. You are what we call a traveling salesman. You have all of your goods strapped to your back, and you travel the country, going from city to city to buy and sell your wares. But, like everyone, you come to one inevitable conclusion. There is one city more beautiful than any other city. One city that is truly worth living in. Of course, that's the city of Delft. So the question you now ask is this: how do I get from Delft to all other cities and back to Delft as quickly as possible? Now, you're quite a smart traveling salesman. You know that if the question was, how do I get from Delft to this city as quickly as possible, you could just use Dijkstra. But now you want to visit all of the other cities and get back to Delft as quickly as possible. How could you do that? Well, one thing you could do is simply take the shortest route available to somewhere you haven't been before. And in a moment, I'm going to give you about half a minute to apply this strategy. But then I also want you to break it. Change just one number so that this doesn't work anymore. And if you have a bit of time left, why not try and think of a strategy that always works? A strategy that, no matter the numbers, gives you the shortest route from Delft through all other cities back to Delft. And if you can come up with that strategy, a strategy that always works, I've got a big prize waiting for you. So let's say half a minute to apply this strategy, to break it, and to find me one that always works. Okay, so let's apply this strategy. Now, this is usually the favorite part of the Open Days presentations for me. It's a room full of people shouting random numbers at me. So to start with, we choose between the 2, the 3, and the 7. So we pick the, and then the crowd would shout 2, great. Next up 4, now 7, 4, 6, 4, 5, and 3 to get us back home. Now, you normally ask the people in the room, okay, is this the shortest route? Right? Is this the shortest route through all cities back to Delft? And normally when I ask the crowd this, they're confused and they don't know. They haven't given it any thought. They just saw the strategy and they ran with it. Never thinking to ask, okay, did we actually solve the problem? Well, fortunately, in this case, we did. If we take a look at the routes we did not select a 7, 2 8s, a 9, and a 10. And the largest one in the ones we did select is a 7. So there's no way I can take one of the routes I selected, replace it with one of the routes I did not select, and end up with a smaller total. I can only make it bigger. So in this case it worked. Great. But I asked you to break it. So hit me. How do we break it? Any suggestions? Says change the 10 to a 1. Yes, excellent suggestion. So what's going to happen? We go here and now we take this one and either we go back to Delft too early or maybe we say, oh, I don't want to go home yet, and I continue my path and I end up over here, stuck somewhere. Yes, so that would definitely break it. Let's see if someone else has a suggestion or if I should give you one more. It seems to remain silent. So I was thinking, okay, how about when I end up over here, I still need to get home. How about I change that 3 into 30,000? Now I don't know what the right answer is in this case, but it's definitely not this. Now I asked you if you can try and come up with a strategy that always works. And if you did, keep it in mind just a little bit longer, that big prize is coming up. But some people already said, well, maybe he means a brute force solution, right? Or mentioned this in chat. Well, let's try that brute force solution. How bad can it be? Well, pretty bad. Say that I can travel from any city to any other. Then I have n-1 choices in the first one and n-2 in the second, meaning that in total, I have the faculty of n options. Well, you are mathematicians, you'll correct me on this. The faculty of n-1 options in total. But trust me, the -1 is not going to matter in a moment. So, the faculty of n options in total. Now, even with an incredibly fast computer that can check 1 billion options a second, and I wish my laptop were that fast, even then, it would take longer than the age of the universe to find the right answer for just 36 cities. So clearly our brute force solution doesn't work. The question then is, what does? And unfortunately, that's where I have to tell you, I don't know. So someone suggested earlier, we have proven that there is no solution to the traveling salesman problem, right? And unfortunately, Sophia, we have not. The answer is, I don't know whether there is a better solution to this problem. And that is the problem. The ultimate challenge in computer science, if you ask me. And we call it P equals NP, question mark. And simply put, it is the question, is there a strategy that always finds you the shortest route through all cities back to Delft? And there's two options. Either such a strategy exists and all computer scientists so far have been incredibly stupid and we just haven't figured it out. Well, I'm a computer scientist. I don't really like that option much. The alternative is that there is no solution. There is no efficient strategy that always works. But if there isn't one, then why can't I prove that? Why can't I show the world that we're not stupid? And I can't do that either. So as computer scientists, we're stuck right here, right in the middle. Every day, someone, likely a mathematician, might wake up to show us how incredibly stupid we've been. Or maybe someday, someone, might be a mathematician, will finally save us and show us that no, it really was impossible. There is no efficient strategy that always works. Now, when I tell this during the open days, many of the faces of the crowd, especially the parents, take on this mode. And I always say that I can't blame them. I think it's awfully nice. A problem that may or may not have an efficient solution and we just don't know yet. But I told you that if you find me a solution that always works, I'd have a big prize waiting for you. And I do. I'll give you $1 million. Well, not me personally, but the question of P equals NP is one of the millennium problems. And solving it, one way or the other, gets you $1 million. Now, if you manage to show that P equals NP, that there is a strategy that always works, come talk to me first. We can make that a whole lot more money. So, is that the reason you should study computer science? Or in your case, is that the reason you should study algorithms and data structures and why you should study P versus NP? Of course not. This is why you should care. Because P equals NP is one of these problems, one of these questions that is not just about computer science. It's about so much more than that. And next week, when we talk about it, I'll show you a little bit about the differences between these classes, P and NP, what they mean for computer science, what they mean for mathematics, but perhaps also what they mean for philosophy, human creativity, and, if you want, consciousness altogether. So, with all that in mind, I'll see you back on Thursday for a tutorial about shortest paths and minimum spanning trees. And I'll see you back next week when we talk about the ultimate challenge in computer science, P versus NP. See you then.